everyone, and welcome to This Explainer. Today, we're exploring an ancient art that is secretly shaping the modern world all around us. Just take a look at the objects in your everyday life. I mean, from the frying pan in your kitchen to the jewelry you wear, right down to the actual engine block in your car. All of these rely on a process that humans have been perfecting for literally thousands of years. I am so excited to guide you through this today because we're going to look at the incredible science of metal casting. We're going to see how taking liquid fire and pouring it into precisely designed cavities solves some of the most complex manufacturing problems on the entire planet.
Okay, let's dive into this. Here's a quick roadmap for today. We'll kick things off with the broad strokes of metal casting, then we'll get our hands dirty with the classic sand casting method. From there, we'll upgrade our molds for better precision, explore the absolutely mind-bending magic of vanishing patterns, and finally look at some heavy-duty, real-world applications.
All right, Section 1, the art of metal casting, shaping liquid fire. Let's start by getting a little bit of historical context on this.
Looking at this timeline, it's honestly incredible to see just how far back this goes. Between 4000 and 3000 BC, early metalworkers were already casting copper using these really simple stone and metal molds. Back then, it was totally a manual, trial and error process. Fast forward to the 1940s, and we start seeing massive leaps in precision with techniques like shell molding. But today is where it gets truly sci-fi. Foundries now use incredibly powerful modeling software. It's a trend called Integrated Computer Materials Engineering, or ICME. Basically, before a single drop of metal is ever poured, computers predict the fluid flow, they estimate the final mechanical properties, and they eliminate defects. It's this perfect marriage of ancient metallurgy and modern software.
To give you an idea of the range here, on the left we have the stunning, lightweight, die-cast magnesium car wheels, and on the right, highly intricate stainless steel components. Now they look completely different, they serve entirely different purposes, and they use totally distinct metals. Yet the underlying concept is exactly the same. You create a cavity, you fill it with molten metal, and you let it solidify. Moving right along, let's jump into Section 2 and look at the most foundational, recognizable, and frankly heavily used method in the world today, sand casting. We're basically building the ultimate sandcastle.
Now, you might hear folks in a foundry talking about green sand, and I need to clarify right now, it has absolutely nothing to do with the color green. Green sand is simply a precisely balanced mixture, 90% silica sand, 7% clay to act as a binder, and 3% water. The word green just means the sand is damp when the molten metal is poured into it. So think of it literally like building the ultimate perfectly moist sandcastle at the beach. This mixture is crucial, right? Because it packs tightly enough to hold a shape, but it's also permeable, which means it allows hot steam and expanding gases to actually escape when that 1000-degree liquid metal hits it.
To hold that sandcastle together, we use a specialized box called a flask, and it's split into two halves. The top half is called the cope, and the bottom half is the drag. And that spot where the two halves meet, that's called the parting line. So, by putting a solid pattern inside, packing sand all around it, and then separating the cope and the drag, we can carefully pull that pattern out. And what's left is a perfectly shaped, empty space inside the sand.
So, the crucial point is how these steps all come together to form a finished piece. Step 1, you pack that green sand really tightly around your pattern. Step 2, you carefully pull the pattern out and carve out your gating system, which is basically the plumbing channels that let the liquid metal flow in smoothly. Step 3, you pour in the molten metal, and Step 4, once it cools and solidifies, you literally just break the sand mold apart in a process appropriately called shakeout. And the real beauty of this whole thing, that sand can be recycled and used all over again.
Now, doing this by hand is great if you just need a few custom parts, but what about mass production? Well, here is a massive vertical flaskless sand molding line. In these super modern setups, machines basically blow and squeeze the sand against a pattern at incredibly high speeds to form these vertical chambers. Then, these molds travel down a long conveyor belt where automated pouring systems just constantly fill them. To put that scale into perspective, this is how a country like China can produce roughly 45 million metric tons of sand castings in a single year. But what happens when basic sand casting just isn't precise enough for the job? Let's transition to Section 3, Precision with Permanent Patterns. Time to upgrade the mold.
Now, what's really interesting about this slide is seeing how every casting method is essentially a trade-off. Notice the balance between weight limits and dimensional accuracy here. Basic sand casting has virtually no limit on part size. I mean, you can cast massive multi-ton machine bases, but the accuracy is really only fair. If you step up to something like shell molding, your dimensional accuracy improves to good, but you're generally capped at around 50 kilograms. And then you have investment casting, which offers excellent accuracy, but again, comes with its own weight and cost limitations. So it's always a balancing act between size, cost, and how precise you need the part to be.
To actually get those better surface finishes like we see in shell molding, we really need to talk about refractories. Refractories are essentially materials that can take a serious thermal beating without breaking down. By using very fine-grained refractory sands mixed with thermosetting resin binders instead of just basic clay and water, foundries can bake a thin, super-hardened shell. This rigid shell holds much tighter tolerances than green sand ever could, giving us gears and engine components that need very little extra machining after they pop out of the mold.
Okay, but what if your part is so incredibly complex that you literally can't even pull the pattern out of the mold without breaking the sand? Welcome to Section 4, the vanishing pattern magic.
This comparison right here is the key to unlocking the most complex shapes imaginable. Everything we've discussed up to this point relies on a permanent pattern. You pack the sand, you pull the pattern out. But if a shape has crazy undercuts or weird internal hollows, pulling that pattern out is just impossible. Enter the expendable pattern. With this method, you leave the pattern completely inside the mold. You don't try to take it out at all. Instead, the molten metal itself either vaporizes the pattern on contact or the pattern is melted out right before pouring. It's brilliant because it completely eliminates the need for parting lines.
Let's see how this builds into the famous investment casting or lost wax process. And fun fact, this is actually a 5,000-year-old technique. First, you inject a wax pattern. Then, step 2, you attach multiple wax patterns to a central column to assemble what literally looks like a wax tree. Step 3, you dip that entire tree into a super fine ceramic slurry, building up a hard outer shell over a few days. Step 4 is where the magic really happens. You turn it upside down and bake it in an oven. The wax just melts and runs right out, leaving a perfectly detailed, hollow ceramic shell. And finally, step 5, you pour your molten metal into that pristine ceramic cavity.
So we've gone from damp sand to vaporizing patterns. Let's anchor all of this theory into reality. Section 5, castings in the real world. Super engines and bionic knees.
Check this out. Here we have a fully automated robot pouring molten aluminum into a lost foam mold. Lost foam is an evaporative pattern process. So instead of wax, the pattern is actually made of lightweight polystyrene foam, kind of like a styrofoam cooler. It's buried in loose, unbonded sand, and when that liquid metal hits it, the foam just instantly vaporizes. The metal flawlessly replaces the exact space the foam occupied a fraction of a second before. And this allows for absolute geometric freedom for the engineers.
And this brilliantly illustrates exactly what that geometric freedom gets you. Over on the left, we have a raw, extremely complex, hollow aluminum engine block that was cast using that lost foam process. It literally looks like a maze of internal water jackets and cylinders. And on the right, that's the shiny, finished consumer product, a really sleek Mercury Marine outboard motor.
The engineering and economics of this Mercury Marine case study are honestly staggering. By switching to lost foam casting, they took what used to be 8 completely separate, individually cast and bolted together pieces, and they combined them all into one single block. By consolidating the cylinder head, the exhaust, and the cooling systems all into one solid casting, they saved a whole kilogram of weight per engine, and even better, they reduced their manufacturing costs by $25 per block. Plus, because the foam pattern included all the pre-designed holes, they eliminated just countless hours of post-cast drilling and machining. That right there is the true power of advanced casting.
Today, it's definitely not just engines. Investment casting is out there saving lives and restoring mobility. You know those ultra-precise, incredibly smooth artificial knee replacements? Yep, they are investment cast. Human joints require the absolute ultimate in dimensional accuracy and a flawless surface finish. And because investment casting can handle high melting point, highly biocompatible super alloys like cobalt and titanium, it is the absolute go-to method for crafting these life-changing medical implants.
Which brings us to our final thought. I mean, we started with ancient humans coring copper into carved stones 6,000 years ago, and we ended up with robots pouring titanium into vanished wax shells for bionic knees. Today, things like additive manufacturing and 3D printing are already being used to print sand molds and complex patterns directly from digital files, completely skipping the traditional tooling phase. So the question I leave you with today is this. As digital printing merges with this ancient art of shaping liquid fire, how are we going to shape the next 5,000 years of metal casting? Next time you look at a metal object, really think about the incredible journey of sand, heat, and engineering it took to get there. Thanks so much for joining me on this explainer. Keep wondering, keep learning, and I'll catch you on the next one.